So for the beginning of today's lesson, what I'd like you to do is just start working away on this warm-up. Just pause the video for 5 or so minutes and work through it, and then you can come back and have a look at the solution that I have for you. Okay, so the solution that I have for you is this. First thing I did was identify 3 different vectors. I have an AB vector, an AC vector, and an AD vector. Now, I found the cross product of AB and AC. Now, remember that this does create another vector, and it creates a normal vector to these other 2 vectors that we have here, okay, which means it's at 90 degrees. Now, I'm going to use that concept that this is a normal vector, and if I do the dot product with my AD vector, it should be equal to 0 if they are coplanar. Okay, because remember the dot product of 2 vectors that are 90 degrees would be equal to 0. And in this case, that's what happens, is it works out that A, B, C, and D are coplanar. Now there is another way of doing this, and maybe you guys attempted it this way, and either way is fine. But I started off exactly the same way. I created my 3 vectors, my AD vector, AB, and AC vector. I took my 2 equations. So what I'm doing is I'm taking my 0, my 8, and -3. And what I'm identifying here is that I'm saying that these should be a scalar multiple. The addition of 2 of them should be a scalar multiple of the other, is what I'm saying. So the addition of a scalar multiple of these should be equal to the -53. And then the addition of a scalar multiple of these should be equal to 60. So those are the 3 equations that I created. Now I'm just going to do the process of elimination. Okay. So I took the second equation, I multiplied it by 8, so I could eliminate my g's and then get down to an h value of -8. I then sub that back into equation 1. So I'm sticking with one of the 2 equations that I used right from the beginning. I subbed it back into number 1 and found my g was equal to -3. Now, if these are coplanar, if I then take my h value and my g value and I sub them into my third equation, it should hold true. And in this case, it does. So just another way, a different way of identifying whether or not those 4 points were coplanar. What we're going to be doing today is we are going to be looking at intersection of 2 planes. And there's 3 different options that we're going to encounter as we're doing this. So if 2 planes intersect along the line, we can say that the system has an infinite number of solutions. And when we do identify that, we can then come up with a parametric equation or parametric equations for that line. So this is the first one. So we have 2 planes that intersect at a line. And because we can identify numerous or an infinite number of points along this line, we can say that it's infinite. Now, we could also say that it has one solution. So in other words, it has one equation of a line or one set of parametric equations that go along this line. If we have 2 planes, let me just state one more thing here. With these 2 planes, the one thing I do want you to notice is that if you were to identify the normal vector of these 2 planes, you would see that they would not be scalar multiples of one another. So they're not parallel in any way. Okay, and that we're going to see that later on when we start working with the problems and we encounter one that looks like this. For number 2, we can see that these 2 planes are exactly parallel. So in other words, their normal vectors would be scalar multiples of one another. Now, we will also encounter the concept of the normal vectors being scalar multiples of one another when we look at planes that are coincident. So in this case, there will be no solution if they are parallel and distinct. They don't lie on top of one another. But if they're coincident, they will share, or the normal vectors will be scalar multiples of one another, and they will basically be sharing a plane. Okay, they will be lying on top of one another. So we're going to look at 3 examples for doing this. And this is our first example. So the first thing I'm going to do is I'm going to identify this as equation 1, and this is equation 2. And I want to identify my normal vectors first. I want to look at my normal vectors because this is going to tell me if they're going to intersect at a line or if they're coincident and parallel. Okay? Or sorry, if they're parallel to one another. So I'm going to say that my normal vector 1 is going to be 1, 4, and negative 3. And then my normal vector 2 is going to be 2, 8, negative 6. Now hopefully you can see that the normal vector 1 is a scalar multiple. We could do a multiple of this to get down to 2, 8, and negative 6. Now one way of showing this, and we've gone over this before, is that if I take the larger of the two, so I'm going to take my x values, and I'm going to go 2 divided by 1, and that gives me 2. Then I'll take my y values, and I'll go 8 divided by 4, and that gives me 2. And then I'm going to go negative 6 divided by negative 3. That also gives me 2. And because all these values are consistent when I divide them, we know that there is a scalar multiple. So in other words, n2 is equal to 2 times n1. Therefore, we know by this information, just by finding that scalar multiple, we know that the planes are parallel. The planes are parallel. So now I want to go through the process and I want to see whether or not they're coincident or if they're parallel and distinct. So I know right from this information here that they will not intersect. It will not be a line of intersection. So I'm going to look at my 2 equations, and I can see that if I take my first equation, and all I'm going to do is multiply it by this 2 value that I have over here. So I'm going to take my equation 1, and I'm going to multiply it by 2. And what I'm going to end up with is 2x plus 8y subtract 6z plus 12 equals 0. Now I'm going to subtract. So I'm going to take equation 2, and I'm going to subtract equation 1. So I'm just going to leave them as they are in the place that they're in. And this is a concept or terminology that I've used before, and I say bracket, subtract it. And this just helps me make sure I carry my negative sign through. But if you see what I got here, 2x minus 2x, that's going to give me 0. 8y subtract 8y, that's going to give me 0. Negative 6z subtract negative 6z, that's also going to give me 0. And then 11 subtract 12, that's going to give me negative 1, which equals 0. So this all says negative 1 is equal to 0. And as you can see, that this is not possible. And because this is not possible, then I can say that these planes are inconsistent, or I could say that these planes, therefore, these planes are parallel and distinct. Okay, on to my second example. Okay, same thing. I want to solve the following system and give a geometric description of the planes. So I'm going to start off the same way. I'm going to identify this as 1. This is 2. And the first thing I want to do is I want to look at their normal vectors. And I'm going to say that normal vector 1 is equal to 5, -1, and 2. Normal vector 2 is going to be equal to -25, 5, and -10. And again, this one here, I can see that n2 is a scalar multiple of n1. And what I can say is, instead of going through the whole process and doing the division, because I recognize it right away, I'm going to say that n2 is equal to 5 times or -5 times n1. Therefore, if one is a scalar multiple of the other, then I know that the planes are parallel. And I just have to determine whether or not they're going to be parallel and distinct, or if they're going to be coincident. So I'm going to take my equation 1. I'm going to multiply by 5 in this case, or -5, I should say, -5. And that's going to give me, or excuse me, you know what? I am going to multiply just by 5. Just by 5. And I'm left with 25x subtract 5y plus 10z subtract 45 equals 0. Now I'm going to take equation 2 and I'm going to subtract equation 1 from it. And again, I'm just going to leave them in place. Oops, excuse me. Leave them in place here. I'll use the same concept. Oh, I'm going to add these, I should say, not subtract them. That is why I multiplied by a +5 and not a negative. So I'm going to add these. And in each case, each term is going to be equal to 0. Now this is always going to hold true. 0 is going to equal 0 in all cases. So therefore, when 0 is equal to 0, this is always going to hold true. Therefore, we have an infinite number of solutions. And the planes are parallel and they're consistent. Okay, so in other words, they lie on top of one another. Okay? So therefore, same plane. All right, and now our last example. Again, I'm going to start off the same way, 1 and 2. I'm going to start off by looking at my normals. So normal vector 1 is going to be equal to 4, 7, -33. Normal vector 2 is going to be equal to 8, 5, -3. And I can tell by looking at these that there's no scalar multiple. If I just look at my x values, if I multiply 4 by 2, I'm going to get 8. So I would have to carry on with that concept of multiplying by 2. Well, if I multiply 7 by 2, that's going to give me 14. So I'm not going to get to what I need. Okay, so there is no scalar multiple for this, therefore not parallel. We can say that there is an infinite number of solutions. Along a line. Now, the process from here starts off exactly the same. I want to look at my two equations, and I want to do elimination, and I want to get rid of one of my variables. Now, looking at the x, that looks like a fairly easy one to work with. So I'm going to start with equation 1, and I'm going to multiply by 2. And what I'm left with is 8x plus 14y subtract 66z plus 34 equal to 0. And now I'm going to take equation 2 and I'm going to subtract equation 1. So my bracket's subtracted here. So 8x minus 8x, that's going to give me 0, which is what I wanted. And then 5y subtract 14y, that's going to give me negative 9y. Negative 3z subtract negative 66z, so it's going to be negative 3 plus 66, so I'm going to end up with plus 63z. And then 7 subtract 34, that's going to leave me with negative 27. Always, always, always look for reductions. And hopefully you see that everything can be divided by 9. So I can divide everything here by 9. And then whatever I do to one side, I got to do the other. Now, I'm going to divide this actually by negative 9. So I make my leading term positive. It doesn't matter. You can do it either way. I just think this might be a little bit easier for me. So I'm going to divide everything by negative 9. So I'm left with y subtract 7z. Oops. 7z plus 3 equals to 0. Now what I've got here is I now have one equation and I have two unknowns, which leads us to a bit of a problem because we're used to dealing with two equations and two unknowns, which would allow us to solve this problem. So what I'm going to introduce is I'm going to say let t, or let z, equal to t. Now, t can be anything. It can be any value. We don't know what it's going to be, so I'm going to say t belongs to any real number. And I'm just going to sub z equals t. And what I'm left with is y subtract 7t plus 3 equals 0. I'm going to rearrange this and solve for y. And I'm left with y is equal to 7t subtract 3. And you'll start to notice I chose t for a very specific reason. This t value is a value that we quite often use when we're doing our parametric equations or our vector equations. So this now allows me to, I can now sub my z and my y back into an equation, and I'm going to say I'm going to sub it into equation number 1. So I'm now going to sub z and y into 1. So 4x plus 7, and I get a sub in what y is equal to. That's going to be 7t, subtract 3, subtract 33z, and I'm going to replace the z with my t value. Plus 17 is equal to 0. And now I'm just going to do a little cleanup here. Okay, I'm going to collect some like terms and I'm going to do some cleanup. So I'm left with 4x plus 49t, subtract 21, subtract 33t, plus 17 equals 0. I'll collect some like terms. I'm left with 4x plus 16t, subtract 4, equal to 0. And again, I can reduce this. I can divide everything by 4. So x plus 4t, subtract 1, equals 0. Therefore, x is going to be equal to negative 4t plus 1. So I now have my 3 equations. I've got my z, I've got my y, and I've got my x, which means I can write my parametric equations. So x at t is equal to, oops, I forgot my t down here, my apologies. And I'm going to write this in the more kind of standard form where I put my constant first. So I'm going to go 1, subtract 4t, y at t is going to be negative 3 plus 7t, and then z equals to t, where t belongs to any real number. And if I want to, I could write this as a vector equation as well. So I'm going to say let r equal to 1, negative 3, 0, plus my t, negative 4, 7, and 1. Okay, so just follow along in the lesson notes, and you guys can see what the homework is. It's going to be on the next page, but that is what we were doing. We were looking at three cases of identifying whether or not two planes were either going to intersect at an infinite number of solutions, in this case a line, or if they were going to be coincident, lie on top of one another, or share a plane, or if they were going to be parallel and distinct.